Ever wondered what derivatives are really for, outside of the textbook? Well, you're in the right place. We're about to take a quick tour through some of the most powerful ways we use them in AP calculus. We're going to see how this one single concept helps us describe everything from motion to making some pretty complex approximations. Let's get into it. All right, so here's our game plan for today. We'll start with what a derivative even means at its core. Then we'll see how that idea describes motion. After that, we'll dive into how to connect changing variables with something called related rates, use derivatives for some really clever approximations, and then we'll finish up by tackling some tricky limits with a very special rule. Let's get started. So before we can jump into all the cool applications, we have to be absolutely crystal clear on what a derivative actually is. At its heart, it's pretty simple. A derivative just measures an instantaneous rate of change. In other words, how fast is something changing at one specific moment? Okay, let's start with a really simple function. We'll call it h of t that just tells us the height of a growing square over time. So if we say h of 1 equals 5, that just means that at the 1 minute mark, the square's height is exactly 5 meters. Easy enough, right? This is our baseline, just a snapshot in time. Now this is where it gets interesting. Here comes the first derivative, h prime of t. This isn't about what the height is anymore. It's about how fast that height is changing. So h prime of 1 equals 2 tells us that at that exact 1 minute mark, the height is actively growing at a rate of 2 meters per minute. Think of it like the velocity of the height's growth. So what happens if we take the derivative again? Well, the second derivative, h prime of t, tells us how the rate itself is changing. So a value of 3 here means that the growth rate isn't staying the same, it's actually accelerating. This idea of a rate is the absolute key to our first major application. And that leads us perfectly into our first stop, motion. This is where we see that function, rate, and rate of a rate idea in its most classic form, the PVA relationship. That's position, velocity, and acceleration. This slide lays it all out. Position, or x of t, is just, well, where an object is. Now take the derivative of that, and you get velocity, v of t. That tells you how fast it's moving and in what direction. Take the derivative of that, and you get acceleration, a of t, which tells you how that velocity is changing. See, it's that exact same layered logic we just saw with our square. Now for a quick but super important distinction. Speed is not the same thing as velocity. Speed only cares about how fast. It doesn't care about which way. That's why we just take the absolute value of the velocity. So a car with a velocity of negative 50 miles per hour and a car with a velocity of positive 50 miles per hour, they both have the exact same speed, 50 miles per hour. So how do we know if something is speeding up or slowing down? Well, it's like a little tug of war between velocity and acceleration, and it all comes down to their signs. If they're working together, meaning they're both positive or both negative, the object speeds up. But if they're pulling in opposite directions, one's positive, the other's negative, it slows down. Okay, let's pause and think about that for a second. What if the velocity is negative, meaning the particle is moving to the left, and the acceleration is also negative? Well, since the signs are the same, it has to be speeding up. It's just speeding up in the negative direction. It's a really common trick question, but the logic always holds. All right, we've seen how one thing's rate of change connects to its position. But what happens when multiple things are changing all at once and their rates are all tangled up together? Well, that's the whole idea behind our next topic, related rates. The classic example, you've probably seen it, is a ladder sliding down a wall. Think about it. As the top of the ladder slides down the wall, the bottom has to slide out, away from the wall. The speed of that vertical drop is directly connected to the speed of the horizontal slide, and calculus gives us the power to find the exact mathematical relationship between those two changing rates. Now, I know these problems can seem intimidating, but there's a really reliable 4-step process. First, and I mean always, draw a picture to see what's going on. Second, find an equation from geometry that connects your variables. Like for that ladder, it's probably the Pythagorean theorem. Third, here comes the calculus. You differentiate everything with respect to time. And finally, you just plug in all the numbers you know and solve for the one you don't. Okay, so we've used the derivative to describe how things change. Now let's see how that same rate of change at a single point can give us an amazing shortcut for estimating the value of really complicated functions. This is all about tangent lines. So the big idea here is something called local linearity. It sounds fancy, but all it means is that if you zoom in really, really, really close on any smooth curve, it starts to look almost perfectly straight. That straight line is the tangent line. And guess what its slope is? It's just the derivative at that one exact point. So we can use this simple line as a stand-in to approximate the more complex curve. Let's see this in action. For the function f of x equals 4x squared, we need two things to build our tangent line at x equals 1. A point and a slope. The point is easy, right? It's just 1, 4. For the slope, we find the derivative, which is f prime of x equals 8x, and we plug in our x value of 1. That gives us a slope of 8. Then we just pop that point and slope into the point-slope formula, and boom, we get the equation you see right here. So why did we do all that? Well, let's say we want to approximate the function's value at a nearby point, like x equals 1.1. Instead of dealing with a whole 4x squared calculation, we can just use our much simpler line equation. We plug 1.1 in for x, and it spits out this very clean approximation, 4.8. So the big question is, how close were we? Our tangent line approximation gave us 4.8. The exact value, if you actually calculate it, is 4.84. I mean, come on, that is incredibly close. In the real world of engineering or physics, this good enough answer is often way easier and faster to find. And here's something really cool. We can even predict whether our estimate is going to be too high or too low. It all comes down to the curve's concavity. If the curve is concave up, kind of like a cup holding water, the tangent line will always sit underneath it, which means we'll have an underestimate. If it's concave down, like a cup spilling water, the tangent line sits on top, giving us an overestimate. For our final application, we're shifting gears to look at a super powerful tool for getting unstuck when you're evaluating limits. This is the famous L'Hopital's rule. You've been there, right? You try to evaluate a limit just by plugging in the value, and you get some bizarre answer like 0 over 0 or infinity over infinity. These are called indeterminate forms, and they don't mean the limit doesn't exist. They're actually a signal that we need to pull out a more specialized tool from our toolbox. And that tool is L'Hopital's rule. The idea is actually surprisingly simple. When you get one of those weird forms, you are allowed to take the derivative of the numerator and the derivative of the denominator separately, and then just try the limit again. It honestly feels like a cheat code, but I promise it's a perfectly valid mathematical shortcut. And, sometimes once isn't enough. As you can see here, after applying the rule the first time, we still get an infinity over infinity form. But that's no problem. The conditions are still met, so we can just apply the rule a second time. And after that second round of derivatives, the limit simplifies beautifully to our final answer of 1/3. And that really brings everything together, doesn't it? Whether we're tracking a particle's acceleration, relating the speeds of a sliding ladder, approximating a complex curve, or solving a tricky limit, the derivative is always answering that same fundamental question. How is this changing right now? It's the mathematics of the instantaneous moment. And that's exactly what makes it such a powerful idea. Thanks for joining me today.